And good evening, 8-bit physics students. Mr. Gerson coming at you here, talking about yet another cool development in the history of quantum mechanics today, the Compton effect. Compton was a physicist down at Washington University in St. Louis, and around 1923 he made a pretty amazing discovery about how photons have momentum. And you're kind of thinking, how can a photon have momentum? It doesn't even have mass. And as it turns out, it does. And Compton wasn't actually the first person to have this idea or come up with this idea. It actually came out of relativity, but he was the first one to really experimentally verify that it does. So let's review a little bit about momentum here. Remember that the momentum of an object that has mass, like an electron or an atom or you or me or a car or anything else, is just its mass times its velocity. Okay? Now, it can be shown from special relativity that the momentum of a photon is equal to its energy divided by the speed of light. Notice if you were to do the units here, kilogram times meters per second, that would end up being the same units here, right? Energy would be in joules or Newton meters or kilogram times meter squared per second squared. And if you divide that by meters per second, you get the same units here for momentum. And remember, the energy of a photon is equal to Planck's constant times the frequency divided by the speed of light. And sometimes physicists are lazy, so they'll write this as two variables instead of three, h over lambda. Remember, 1 over lambda could be written as f over c because of course, the relationship c equals f times lambda. Okay? All right, so let's talk about the Compton effect. This is the background knowledge that we need to know, and let's talk about the Compton effect. Here's what happens in the Compton effect. The Compton effect is a collision between a photon that doesn't have mass or intrinsic mass or rest mass and usually another object that does. For instance, an electron. The problem we're going to work with deals with a stationary carbon atom, but many times it's a photon bouncing off an electron. Well, let's see if we can come up with expressions for the energy of this photon and this electron. Well, the energy of this photon here would just be h times its frequency, the initial energy anyway. And the momentum would be Planck's constant divided by the photon's wavelength, all right, lambda sub I. Now, the initial energy of this electron would be its kinetic energy, and that's just zero because the electron's stationary. Likewise, the momentum would be zero because our electron's stationary. So this is before the collision. Now, after the collision, the photon gets scattered. That is, it comes in and it bounces off and it gets scattered. So sometimes you'll hear the Compton effect referred to as Compton scattering. Okay? So what happens here? Now this electron acquires kinetic energy, 1/2 mv sub f squared, and momentum mv sub f. Okay? The photon now has less energy, okay? Its frequency will have gone down, and some of its energy will have gotten transferred to the electron. Likewise, it will have a little less momentum, all right? The photon will have gotten a little bit longer of a wavelength, a little bit less energy, because it will have given some of its momentum and energy to the electron. Now, the details and the algebra of this get a little complicated, but if we say that the photon scatters off of the electron at some angle phi, we can use good old algebra and good old conservation of energy and conservation of momentum to figure out how much energy the photon will have lost and how much momentum it would have lost. fast, okay? Now, the algebra here is complicated, but the physics is not, okay? All I'm doing here is talking about conservation of energy and conservation of momentum. As soon as you define a photon to have energy this and momentum this, you can apply conservation of energy and conservation of momentum just like you would in any problem. So if I were to add up the initial energies, they would have to equal the final energies. And if I took the vector sum of the initial momentums, remember momentum's a vector, that would have to equal the sum of the final vectors of the momentum here, okay? So conservation of energy and conservation of momentum, those two topics we spent so much time on in Try 1, can be combined to come up with, dun dun dun, the equation of the Compton shift, or the Compton effect. So if I do a lot of algebra here, I will find that when the photon scatters off of this electron, the change in wavelength of the photon, and the photon will always get a longer wavelength because that means less energy because it's losing energy to the electron. The Compton shift, or the change in wavelength of the photon, will be equal to this expression here, where h is Planck's constant, m is the intrinsic mass or rest mass of the electron or whatever particle we're scattering off of, and phi here is the angle that the photon bounces off of. Okay, that seems complicated, but let's do a little sample problem here, okay? So in problem number 30, I have a X-ray photon, okay? And the X-ray photon has an initial wavelength of 0.120 nanometers, okay? So this is a lot shorter wavelength than any of the visible light. Remember, visible light would have a wavelength of at least 400 nanometers, right? And this X-ray photon comes across a carbon 12 atom, okay? So this is kind of before the collision, and then after the collision, the carbon 12 atom gets shot off over this way, and the photon scatters this way, okay, the X-ray photon. Now, I can figure out the change in wavelength of the photon from this initial wavelength here before the scattering to the final wavelength here. And by the way, this wavelength should be longer than this one, okay? Okay, so the change in wavelength of this X-ray should be equal to h over mc times 1 minus cosine theta. And I am going to do part B for you here. And in part B of this problem, theta is 45 degrees, right? So if I plug, I'm going to let you do part A and C on your own here. So if I plug in for the change in wavelength of this X-ray photon scattering off of this carbon atom, I am going to get Planck's constant, h, times 1 minus square root of 2 over 2, because that's the cosine of 45 degrees, times the mass of the carbon atom, which would be 12 AMUs, right? 12 times 1.66 times 10 to the minus 27 kilograms, times the speed of light, okay? And if I plug all of that in, I get a Compton shift of 2.43 times 10 to the minus 12th meters, or if you prefer, 0.002 meters. So the photon would go from 0.12 nanometers to about 122 nanometers. So about 1% increase in the wavelength of the photon there. All right, so that's part B. I'll let you guys take over for parts A and C. All right, nice work, physics students. We'll see you tomorrow.